This chem tube, if you can go up there, you see a molecule twirling around, and that's pentadiene, which is your diene of the Diels-Alder, and then you have maleic anhydride, which is the Diels-Alder dienophile, and it's forming a new cyclohexene product here, which is bridged. It's bicyclic. This is a harder problem, and it highlights the endo versus exo. Endo will be favored. We'll get into the details, of course. That's the main topic today, the Diels-Alder reaction, and we will use ChemTube 3D here, and I think we're using it also for quiz 1. So you'll have to go to ChemTube. It's a free product. It's developed in Great Britain, I think at the University of Liverpool, and they have a number of organic animations. And the Diels-Alder one is well represented. There's a lot of examples of the Diels-Alder. You go to ChemTube, and then you mouse over the organic button here, and I think, yeah, Diels-Alder, click on that, and you'll see a whole bunch of Diels-Alder examples, and a couple of those I think you'll need to go and look at. But you can manipulate this with your mouse, and you have controls over it. And the key thing here is when you do it, you need to click on the arrow to start the animations here. And if you click on this one over here, that's the exo pathway, where the electron withdrawing group is away from the diene, and this is the endo pathway. And I've got models here today too. We'll use handheld models to figure that out also. But the great thing about ChemTube, not only is it free, you can use it on any device, your pad. In fact, if you have a pad or a computer today, you can have that up when we go through a couple examples. And it works on your smartphone as well. So you can do it during sacrament meeting if you want to. No, I don't recommend that, okay? But in any way there, you can be using that. All right, let's go to the board here and start working some of the problems and go over the key aspects of the Diels-Alder reaction. So this is a famous reaction. Otto Diels and Kurt Alder won the Nobel Prize for this reaction. It's kind of unique because the Nobel Prize is usually just awarded to the principal investigator, usually the professor or the senior scientist, wherever. But Alder was a graduate student in Germany in 1928 when this was discovered. Caused a great stir in the chemistry community, a brand new type of reaction. Reactions up to this point were always heterolytic in nature, anions and cations, acids, bases, charged intermediates, whatnot. Here it's just a diene reacting with a dienophile, which is another alkene, really. Okay, it was originally called the diene reaction. And it makes cyclohexene, which is an amazing product because it forms a ring, and it forms what? 2 new bonds, okay? And it can form stereocenters. So there's a lot of versatility to this reaction. A couple things to point out here is the terminology. Here's our old friend butadiene. That's the topic here in chapter 16. It has to be in the S-cis conformation. So I'm drawing it here S-cis. You can rotate around that bond. Remember, it has double bond-like character and single bond-like character. So we can rotate around there. The barrier's about, what would we say, 6 to 4 kcals per mole. It's pretty low. Most of the time, butadiene's going to be in the lower energy, S-trans, right? But if it can be in S-cis, then we can do the Diels-Alder, and the mechanism's very easy. That's the nice thing about the Diels-Alder reaction. Just push those 6 electrons around the ring, and you'll make this new bond here, and that bond there, and you see this pi bond just gets moved over, okay? So mechanistically, it's pretty simple. Couple things to point out here is this reaction favorable? Let's see, what's the change in enthalpy? Because we're making a couple sigma bonds. We go from 3 pi bonds down to 1, right? So we're going to have to break 2 pi bonds, and that's worth 60 kcals each. So 2 times 60, that's going to be breaking, what, 120 kcals. And then what do we get back out? Well, we get the 2 sigma. And what are sigma bonds worth? They're almost 100 kcals, right? Or 90 or so. So what is that? You're going to be getting out 180. So let's see, what is this? Minus 60 for the change in enthalpy. So that's pretty good. That's exothermic by quite a bit. Did I do that right? 180. Okay, yeah, question. Yeah, it does form the pi bond here. And so technically we're breaking 3 pi bonds, but we're getting 1 back. So that's why I say overall we're just breaking the 2. Does that make sense? Sometimes I mess these numbers up. It's significantly exothermic. It's giving off a lot of heat there. But it's got an issue with the conformational control. It's got to have a diene that can be in the S-cis conformation. It's better if it's locked in the S-cis. But if there's a diene that's locked in the S-trans, it won't participate in the Diels-Alder reaction. So they've got to come together here in a concerted manner. And that's actually the mechanism as we push this around here. It's called a concerted mechanism, like I said, which is unique. So far we've looked at heterolytic, ionic type things, but doing that reaction there. It's part of a general class of reactions called the pericyclic reactions. There's a lot of other type of reactions in this family. The Diels-Alder is just one. It's called a 4+2 cycloaddition. That's the technical term for it within the pericyclic class of reactions. There are actually 2+2 cycloadditions, which would look like this. Those tend to not be very favored. As you can see, that would be a butane product with 2 pi systems coming together and the strain associated with this. But you can actually do these type of reactions, especially if you shine light on it. In fact, this 2+2 reaction is the basis for cancer formation in a number of cases, especially skin cancer, which involves thymidine bases dimerizing in a 2+2 manner with visible light. That's why you have sunblock if you don't have much melanin in your skin, whatever. But there's a number of these pericyclic reactions. Maybe I'll show you one more here, pericyclic rearrangement, which is also concerted, which just involves rearrangement of pi bonds and sigma bonds. This is called the Coppery Arrangement, which goes to this type of product, which just involves breaking a couple pi bonds there and switching the sigma bond over here. But don't worry about these other classes. We're just focused on the 4+2 Diels-Alder reaction and the aspects to it. Now, don't be deceived by how simple the mechanism is, this concerted mechanism pushing electrons around. The stereochemistry is the tricky part. And I'll summarize the key issues you got to be aware of. I'm already mentioning the Endo Rule with the Chem2 example there. It depends on how the diene and the dienephile come together, okay? If there's stereochemistry in the diene or the dienephile, that stereochemistry is manifest in the product, okay? I'll show you examples of that. That's the simplest thing. Like if you have a trans dienephile, if there's like a methyl and some X group here, the X group and the methyl will end up trans to each other, okay? That's relatively easy to see in the transition state when the two come together. The Endo Rule is a little trickier. In the transition state, the electron withdrawing group, in fact, will need a significant withdrawing group to make the dienephile more electron deficient. We'd like to have a partially positive end on our dienephile, which makes it more attractive to the electron-rich diene. Okay? So these partial charges can be important. And we want to put the X group underneath the diene And that will be the trickiest thing we'll look at when we examine the transition state. But that's only important if we're generating two stereocenters, okay? The X group can be a stereocenter, but we also need a stereocenter at the allylic position in order to even invoke the Endo Rule. A lot of times we don't need it. If there's not a stereocenter generated at the allylic position, the Endo Rule, it's actually being manifest in the transition state, but you don't see it in the product. You don't need to worry about it. But this Endo Rule can be a tricky thing for new students to keep straight. But we'll show you the transition states and help you out with that. But yeah, it's really only an issue if you got this type of arrangement here, okay? And then regioselectivity, this will be another thing where we'll have to look at an asymmetric dienophile, and then we'll have to look at these resonance structures and match up the partially negative end, the more electron-rich end of the diene, with the electron-deficient end of the dienophile. But that'll be pretty straightforward if we just examine some resonance structures for it. But those are the trickier aspects of the Diels-Alder reaction. Okay, we're going to go through this now and hopefully keep this straight. Now, what do we mean by these electron withdrawing groups? Okay, so let's keep that up there. If we have our diene and react it just with ethylene, or if we just have an alkyl thing like propene or butene, we'll get no reaction. We need to have an electron withdrawing group. And what do we mean by electron withdrawing group? So by resonance, it'll make this end partially positive. So let's look at a typical one. How about if we have this guy? It's called acrolein, the common name. It's an unsaturated aldehyde, right? We could look at its resonance structure, and we'd have this is the important thing. Okay, and so we see this partial positive charge at that position. That makes it more attractive to the diene, and we can push electrons around there. And what's our product? Well, it's the aldehyde with cyclohexene on it. Okay, we don't need to worry about stereochemistry yet. That is a stereocenter. Okay, and there's actually two transition states. And we can form both the D and the L. So we can just say plus minus or DL or just say it's racemic. If you remember your stereochemistry there. But we really don't need to specify because if we just leave it undefined in this simple case, there's no other stereocenters relative to it. So that's fine. But you get a very good yield of this. You can get 90% yield of that and that would be fine. Let's look at some other examples here. What if we have butadiene with this dienophile? Okay, so that's called an anhydride. We'll get into those type of functional groups before. Again, the mechanism's relatively easy here. Just pushing around the ring that way, and we get product, which would be that. We get a good yield of that. Always identify the cyclohexene. That's the key product of the Diels-Alder reaction. Everything kind of goes along for the ride. Question. There's two hydrogens here. And they end up in the product. Are they cis to each other or are they trans to each other? Now we start to get into the stereochemistry of things, right? Should we take a vote? Who says they're cis to each other? Let's see if you're awake. Okay, one guy, two guys, three. Okay. How many say they're going to be trans to each other? Be brave. Okay, nobody. Okay, maybe you're asleep or not brave enough. We'll see. Let's examine the transition state and see what we're talking about here. So when we talk about the reaction, we have our diene and we have our dienophile. And, we've got our pi bonds here. I'm drawing the p orbitals there. And then we're overlapping, you see, with the pi bonds of the dienophile. So when these come on there, where are these going to be? Let's see, we could have this transition state here. We've got this. We've got those hydrogens on there. And so as long as we interact there, what's our product going to look like? Well, it's going to look like this, right? You're going to have that. Okay, so we make these two bonds, the sigma bonds right there. But it's the overlap, right, directly of the pi system here of the dienophile and the pi system here of the diene. So I'll ask the question again. These two hydrogens here, are they cis? Who says cis? Okay, a few more. You either woke up or you're buying into this, maybe. Who says still it could be trans? Be brave. Okay, nobody. Okay, we kind of lost everybody there. And you see, these will be down, right? Because they're cis to each other here in the starting material, right? And so that's the first level of understanding of stereochemistry. Any stereochemistry of the starting materials will be manifest in the product, okay? So cis goes to cis, okay? Let's look at some other dienes. There's actually a whole bunch of them, and they're all the ones we'll look at. We'll have conjugation to a pi bond that has a more electronegative atom. So like with the aldehyde, we could draw that resonance structure, partial positive charge here. You can do ketones, of course. Esters. So methyl ester with a alkene on it. Again, the carbonyls conjugated to those. We've got the anhydride we showed there. Quinone. In fact, quinone has two. We could actually do a double Diels-Alder reaction here. Notice there's two carbonyls conjugated to the alkenes. Quinone is actually an especially reactive Diels-Alder dienophile. So quinone, cyanide. Again, that's a triple bond, but it's conjugated through there. You can push the electron density over to nitrogen. So you can practice those resonance structures. How about nitro? Yeah, that nitro one turns out to be a very good Diels-Alder dienophile also. All right, let's look at a complicated example. Yes, I like to jump into the complicated one right away because we'll point out some issues here. Now, to point out the cis relationship here, cis to cis product, so yeah, you would draw these both down or both up. It doesn't matter. There's symmetry in this molecule, right? It's achiral. But the two hydrogens need to be cis to each other in either depiction. You could flip this over and have them both up, okay? You would not want to draw one down and one up. That would be impossible for the Diels-Alder transition state. But the way we drew it here, we had the carbonyls out here. How come we didn't flip it underneath and have the carbonyls tucked under the diene? That would be the endo transition state. We're actually drawing the exo here. But we're going to back up and look at some simpler examples here. Here it doesn't matter. This isn't a stereocenter at the alloy position, so we don't need to invoke the endo rule, okay? The transition state, if there is a stereocenter here with a more complicated diene, then we have to examine the endo rule and make sure we apply it there. So let's look at some other examples here. A little more complicated diene, and that is this. Cyclopenidine. In fact, we saw cyclopenidine before when we talked about 1,2 versus 1,4 addition. It's, the cyclic thing with pentane, cyclopentane, and the two alkenes are within the ring like that. So what do you notice? It's locked as S-cis, right? This is one of the most reactive Diels-Alder dienes. These reactions can go at room temperature. As soon as you expose that to a good dienophile, this reaction I'm going to show you is going to go like a shot. Okay? It's a little more complicated. Well, we'll use that same acrolein, same unsaturated aldehyde. And how's this reaction going to go? Well, we can do our Diels-Alder transition state here. Okay. But notice we have a methylene, a CH2, intervening there. That's okay. Draw your cyclohexane product, and then whatever else is on there. Okay? So let's, have the aldehyde down there. We could have it up there. Doesn't matter. Do you see the cyclohexene? That's the important thing to see first, right? Here it is, your 6-membered ring. But notice you still have that 5-membered ring right there. And look, we got a new 5-membered ring right there. So an example like this points out the versatility and the utility of the Diels-Alder reaction. You can form multiple rings, okay? And you can have intramolecular versions too and form polycyclic compounds. So this opens up a lot of possibilities to make much more complex products from these simple starting materials. But what does the product look like if you tip it on its side? Looks like this. Okay, it's called norbornene or norbornane if this alkene wasn't here. That's a common polycyclic structure in a lot of plant materials, essential oils, a lot of very fragrant compounds. So this aldehyde product actually has a very pleasant smell. But norbornene, don't worry about that name. It's just this core structure that we're forming here. You see the 5, and then where's our 6-member ring? It's right here. 1, 2, 3, 5, 6. This bond's behind this one in the front. So we're kind of tipping this up on its side. Okay? And we have stereocenters here and here, right? And we're forming a new stereocenter right here. So we've got, this hydrogen here, and then relative to this aldehyde, what is its position relative to the alkene over here? I'm actually drawing the endo product right now, okay? That's actually the major one, 10-to-1 over this one. Let me draw it the same way, okay? And if we have the aldehyde out here, that's called the exo product. Endo is always major. Usually it's about 10-to-1 to the exo product. There's some good reasons for that, and we'll get to that in a second here. Let me show a couple other stereochemical issues first. They're a little easier to deal with. But we need to wonder why, okay? And maybe we could look at the handheld models right away to begin to think about that. So here's cyclopentadiene. Here's our aldehyde. The red ball is the carbonyl, the aldehyde. So we can either have it tucked underneath like this. This gets a little complicated. ChemTube probably does a better job. Okay, see the aldehyde pointing down there? And see the methylene here? Right here, the methylene. Then you go to the product. You can see where I have my hands. So those are the new sigma bonds that are formed. And that's why this is more complicated, right? It's a little bit tricky to see the cyclohexene. And then it's that relative stereochemistry. See the aldehyde's pointing down, okay? That's actually called the endo process. And this would be the exo. Let's go back there. Okay, see the aldehyde. I switched the stereochemistry because I switched the facial selectivity, it's called. I brought together the opposite face there. And then that is this, okay? So those are different, aren't they? You see here, the aldehyde, or the electron withdrawing group, tucked underneath. You see the red ball is close to this pi system back here, underneath the where the diene is, okay? Here it's away from the pi system. of the diene in the exo transition state. Okay. That's the toughest concept. We'll get back to that. I want to go back and do a couple of more simple concepts right now. So let's look at butadiene, the simpler one. And let's put a couple groups on here. So here's a carboxylic acid. It's called cinnamic acid. Cinnamaldehyde, if this was an aldehyde, that would be the essence of cinnamon. This is the oxidized form. Carboxylic acid. We've got a trans dienophile. Okay. Go ahead and push your electrons around the ring. There's our transition state. Yeah, the mechanism's easy for the Diels-Alder. They're all the same. The tricky part's the stereochemistry. Okay, but I listed them up there, the three key aspects, and we're getting to the endo thing. But this first one is to point out here that if this is trans, what's the product going to be? Well, cyclohexene, phenyl up, and carboxylic acid down. Okay. And you can see that if you want to draw the transition state with three-dimensionality to it, we're going to have the carboxylic acid tucked underneath. The phenyl group, the benzene, is actually exo to the transition state, and there's going to be our product forming. So you see this hydrogen here. You can focus on the hydrogens too. Sometimes they're easier to keep track of. They're trans to each other, right? We started with the trans cinnamic acid. So you see they're trans. That one's down. This one's up. Okay. So the stereochemistry of the starting material is translated directly into the stereochemistry of the product. This begs the question. What if we start with the cis cinnamic acid? That's known. Let's see. Plus cis. We're going to get the same product? No, you can tell. In fact, let's just modify our thing here, right? Transition state. The great thing about the chalkboard, I can just modify that. Bring that together tucked underneath there. And what's going to be our product? Well, they're going to be cis to each other, right? Our acid will be down, and our benzene will be down. Okay, so we'll get the cis product here. So yeah, the Z goes to cis here, and the E, or the trans, goes to the trans product. Question on that. You can see that by invoking the same transition state, whatever groups are on the dienophile, or on the diene for that matter, are translated directly into the product like that. All right, let's see. Let's do maybe one more. Maybe this is a simpler one. It points out connectivity, though, I think. How about if we have quinone and we put those two together? Now we have butadiene with two methyl groups on there. Okay, so we have a lot of functional groups. And let's see what we need to worry about here. Well, there will be our transition state. So our alkenes moved over here. And where are those two methyls? Well, they're going to be right there. Okay. And then where's the rest of our molecule? Quinone will be here. And let's see. We have two hydrogens here. Are they going to be cis or trans? They started out cis to each other in the starting material. So what are they going to be here? They're both going to be either up or down. Doesn't matter whether they're both down or both up. That's the same molecule. You have symmetry there. Okay. But I think you could draw the transition state. We would draw actually the favored endo transition state. We wouldn't need to worry about it. For most of the examples at this level, the beginning example, you don't need to worry about whether it's endo or exo. You need to worry about, though, the stereochemistry on the diene. Okay? And then make sure you get the right thing there. Questions on these examples so far? Okay, pretty straightforward. All right, should we get into the toughest topic, the Endo Rule, and hopefully figure out why that works? Yeah, so let me give you some example here where I've got the numbers for it, and that'll be with the cyclopenidine again, and the unsaturated ester. Okay. And the first thing to consider is just, what's our product here? I always just draw the cyclohexene first. If it's a Diels-Alder, it's going to be there. And then add in the other stuff. So we have this methylene that's bridging between the two rings now. And it's still there. And then where do we put the ester? And that's the key. Make sure you know which bonds we just formed for the Diels-Alder, right? So do we put the ester here? No. Do we put the ester up here? How about up here? How about over here? Where does the ester go? Does it go right here? Okay, I saw a few more heads. So the ester should be right there. And that can be a tricky thing of these more complex Diels-Alder reactions. Make sure you have the functionality on the same bonds where they started out. Okay. The mechanism is relatively simple, but sometimes the connectivity can get confusing. Okay. Let alone the stereochemistry, which we're getting to now. Okay. Let's see. The product is actually this. Is major with this down. Okay. And you can view the three-dimensional view of it like this. And if you want to draw that hydrogen in there, you can. Notice the hydrogen and the methylene are cis to each other on this six-membered ring, right? And the ester is down here underneath where the diene is. That's the endo product. And it's formed in 75% isolated yield. Okay. Very good reaction. It goes at room temperature. Sometimes you have to heat them up if you don't have a good electron withdrawing group here. But this one does go at room temperature. And that's an amazing thing, right? Usually we have other reagents or other things for the conditions. When you bring these two together, if they're locked S-cis, which makes this faster, and the withdrawing group allows this reaction to be spontaneous at room temperature, which is kind of amazing. But you also get some of the exo, which is this. Actually quite a bit, 25%. Now for a quiz or a test, if you just put the endo product, make sure you know which one it is. You can represent it like this, which is a flat 2D thing with the wedge and the dash, or you can draw it with three-dimensionality to it, but just make sure you have it straight. Here's another thing to be worried about. Is this a chiral molecule? Yes. Is this a chiral molecule? Yes, there's three stereocenters. There's no symmetry here. So this is formed as a mixture of enantiomers. They're both racemic. Another level of complexity. Which means there are actually two endo transition states that lead to the two opposite enantiomers. But it's this relative stereochemistry right here that's the rub now. Okay, why endo? Let's see if we can rationalize this. Let's draw the transition states. And we're going to start with endo first, where we've got the withdrawing group, okay, electron withdrawing group, which allows us to draw that resonance structure with this with a partial positive charge, which makes that more attractive to the electron-rich diene, by the way. But we've got it tucked underneath here so that there's actually this extra overlap between the pi system of the withdrawing group and the bottom of the diene. That's called secondary orbital overlap. Okay. That's the rationale that your book uses for the endo transition state. Because endo, this is a relatively big group. The alternative exo is putting the smaller hydrogen under the diene. Sterically, just in 3D space, that would be more efficient. But electronically, we have this extra overlap. These are pi bonds, right? And so are these on the withdrawing group, okay? So you get this temporary overlap. It's kind of like hyperconjugation when we talk about stabilities of carbocation. Kind of mysterious, but actually, the latest theory shows that the Endo Rule is actually dominated by a solvent effect. It's a smaller transition state structure to solvate. It's more compact. It's more efficient to have this tucked underneath. So at the withdrawing group under, that's what the Endo Rule means. And you see that then generates this product. We've got that down, right? So look, the hydrogen ends up in the exo position. The withdrawing group is in this underneath position there, okay? So we need to do what? We need to compare that to the exo one. So if we have exo, we've got same arrangement of the diene and the dienophile alkene, but now the withdrawing group's out here, okay? And the hydrogen's underneath, right? So there's our transition state. What does it lead to? Well, it goes directly to that. I already got it there, okay? So you can see the methyl ester here is out away. Electronically, it's not communicating with the diene part. It's in this exo position now away from the diene relative to the diene. And that sterically actually can be more favored. But notice this is a more elongated transition state. This is a more compact or spherical transition state. So the solvation, the entropy of solvation, and I'm not going to get into that. The book mentions a secondary orbital interaction, and we'll stick with that argument, okay? But if you have a choice and it is needed, make sure you show the endo product. And it's really because at the allylic position we have a stereocenter, and of course where we have the drawing group's a stereocenter. We had a number of dienes where there wasn't a stereocenter, with butadiene and the other ones, okay? It's not an issue. But if we've got a stereocenter here, then we have to invoke the Endo Rule. Questions on endo versus exo? Let's do it with the models here. So here it is again. Here's our ester. The methyl ester is the red ball. And let's go ahead and start to form our sigma bonds. Okay, there's our transition state. And I've got the product here. Let's see. There it is. And the red ball. So, yeah, there it is. Also right there, there's the endo product. Okay. And if we did exo, what would that look like? Where we'd have, see the ester now away. It's not underneath the diene. Underneath the diene part is over here, right? So that's this depiction here. And you see the red ball is out away from the underneath the diene. And that leads to this product here, which looks like what? Okay, yeah. Make those models, and again, it's a little tricky using the handheld models because you got to have models for the starting materials, and then have a model if you got enough atoms in your kit to go to the product. But you see the norbornene system here. You see the 6-6 ring, and then or the 5-5 ring. Sorry, and then the 6-membered ring is right here. See that 6-membered ring? That's the tricky part. Okay, we've gone to the very tricky examples, I think, of this. Now let's do an even harder one. Keeping these things in mind, let's see, how about this? Now we've got 2,4-hexadiene, I think. And we got stereochemistry on the alkene. This is what? The trans or the E, and this is also the E. Okay. Is this the S-cis conformation now? Yeah. We can rotate around here, right? But that's S-cis. So just analyzing the diene is tricky in this case. Let's see. This is in equilibrium with the S trans, right? Which one is going to be the Diels-Alder conformer? It's this one here. Notice we still have E here and E here. I didn't isomerize the alkenes, okay? I just rotated around this bond. That's kind of the tricky part of some of these highly substituted dienes. Now let's see, which reaction are we going to do here? Oh, same one. Let's do our ester. And this again, you have to heat this up a little higher. This is not locked S-cis like cyclopenidine, so this has to be heated up 50 degrees. It takes a little while to go. But when it goes, we've got the Diels-Alder reaction right here. Okay. And what's our product? Cyclohexene. And we've got some stereochemistry to worry about. We've got 3 stereocenters. How are we going to figure this out? 3 stereocenters? That's 2 to the 3 power. That's 8 possible stereoisomeric compounds. Yeah, so you see the complexity here. But let's invoke the Diels-Alder transition state. Okay. And put our methyl groups on there. Okay. And notice there's still trans or E, right? And then we've got our diene. And look, what transition state am I doing here? Is this endo or exo? Endo, very good. That's the major one. In fact, the selectivity here is 6 to 1 for the endo. Some of the exos forming. But this would be the endo. And notice that kind of helps to add in the hydrogens here. Can you already tell what the stereochemistry is going to be here? Let's see. And let's redraw it, the product here with the same conformation as the starting material. So did I get the methyls right? The 2 hydrogens are both up, you could say. The 2 methyls are both down. And then this hydrogen you see is up. And then what? This ester is tucked underneath. Well, oh, don't forget about the alkene. Question on this so far? Yes, please. Yeah, because here, yeah, the question is the withdrawing group endo would be down here, because then you can see you get some extra overlap there. Yeah, so always put the withdrawing group tucked underneath the diene when you draw the transition state. So you can kind of see that in 3 dimensions maybe, that this ester would be underneath. And not here. If it's out here, that'll be the exo transition state. And then electronically, you see it's very remote from the diene. Practice it, drawing it out and keep things relative, orientation wise. Don't keep reorienting or tumbling things around. Molecules can do that, of course, but for your orientation and for your own sanity, keep the orientation consistent. You can follow, my lead, and I'm following how the book does it as well. So I think that kind of keeps it straight there. And it's that relative position, right, between the diene, and that's where the alkene ends up. The diene becomes an alkene here on the back. You see that's underneath where that is. So if we pull this out and look at the 2-dimensional thing that we might draw on the quiz or a test, what do we have? The 2 methyls down. And what? The ester. Is the ester down or up? Relative to those 2. It's down also. Okay. Yeah. So we have all of them down. And you can see all these hydrogens. You don't have to draw them in, but to be thorough, maybe you can. You see there they all are. They're all on this same face up here. This is a very hard example because you've got to keep track of the trans geometry of these two alkenes, right? Transition state, endo, and then pick out what, one stereoisomer out of the possible 8? Well, we could have this transition state where we have the ester on the other side. This is also endo. And look what this one goes to. It goes to this. The ester down, up, methyl group still down. Okay. And what if we flip this over like that? We get the enantiomer of that. Sorry. And there we have the methyl up, and look, the ester would be up right there. So look, those are the two enantiomeric forms of this, where they're all cis to each other. And that's what? The DL pair, okay? Because, you know, these are both achiral, both of these starting materials, so we can either bring them together like this endo, or we can have the ester over here, endo, like we did before. One will go to this enantiomer, this arrangement, transition that goes to that enantiomer. And they're both the same energy. They're both endo with the right geometry of the alkene. And yeah, this is form racemic. But this is, what did we say? Yeah, endo, it's 6-to-1 over the exo. So we haven't drawn exo yet. Let's do exo right here. Sorry. Exo would have the ester right there. Do we have time? Yeah, 1 minute. Let's see if we can do it. Okay, we still have those there. And then we have our ester here. So we have a hydrogen up, hydrogen down. So what's that look like? If we draw it 2 dimensions flat on the board. The two methyl groups are cis to each other, and that's because they were trans on the diene, right? And then what about our ester? Ester right here. That is the exo. It's less favored, okay, because the transition state does not allow for the secondary orbital. Okay, now that's the toughest concept, okay? So we'll leave it there for today. Make sure you work enough of those examples there in chapter 16